For decades, we viewed the universe as a slow-growing garden. Starting from the Big Bang, stars and galaxies were expected to form gradually. We expected to see tiny, infant galaxies, nascent clusters of stars just beginning to ignite in the early dark ages of space. But reality proved much stranger. We discovered massive, fully mature galaxies existing when the universe was still in its infancy. These are the universe breakers. These glowing red dots captured by the James Webb Telescope contain as many stars as the Milky Way, yet they appeared far too early in cosmic time. This discovery forces us to rewrite the history of our cosmos. How can a fully grown garden exist where we thought the seeds had barely been sown? In early 2023, astronomers utilizing the James Webb Space Telescope identified a collection of 6 galaxies that shouldn't exist. These objects, found roughly 500 to 700 million years after the Big Bang, are absolute monsters. This creates a massive paradox. Gravity simply did not have enough time to pull this much matter together, yet these galaxies were fully formed. They defy the slow build theory of the early universe. Our cosmological models must now account for this unexpectedly rapid assembly of matter. Lambda CDM is the standard model of our universe. It functions like a cosmic speed limit. For decades, this slow build theory suggested that early galaxies were small and primitive. However, gravity has a speed limit. At just 300 million years after the Big Bang, gravity simply hasn't had enough time to pull sufficient matter together. This expansion model confirms that mature, massive structures should be impossible this early. How can we be certain that these distant galaxies are truly massive and not just measurement errors? The answer lies in the James Webb Space Telescope's powerful instruments, NIRCam and NIRSpec. The SEER survey used NIRCam to capture high-resolution images of these objects. While initial mass estimates were debated due to dust, NIRSpec provided the definitive proof. Spectroscopy breaks light into its component colors, revealing chemical fingerprints. By identifying these signatures, astronomers calculate exact distances and confirm the massive stellar population within these early galaxies. Recent spectroscopic follow-ups have confirmed their massive, mature nature. We are no longer looking at data glitches. We are looking at a fundamental challenge to our current models of how the universe began. One leading theory suggests that the early universe was structured by dark matter. This invisible scaffolding acted as a cosmic web, a hidden frame for everything to come. These filaments channeled vast amounts of hydrogen gas toward dense nodes. This funneling effect accelerated the rate at which gas could collide and collapse into stars. By concentrating matter far more efficiently than gravity alone, this scaffolding essentially allowed the universe to cheat its own speed limit, building massive galaxies in a fraction of the time. Early supermassive black holes acted as powerful engines, rapidly accelerating the growth of their host galaxies through a process known as feedback. As gas fell into these black holes, they released immense amounts of energy and radiation into the surrounding environment. This energy violently compressed nearby gas clouds, triggering a star formation frenzy that allowed stars to ignite much faster than gravity alone would permit. By creating this frenzy of star creation, these black holes acted as a catalyst, rapidly building the massive galaxies we observe in the early universe. The radiation and high-speed winds from these black holes effectively sculpted the galaxy, pushing gas outward and fueling the birth of dense stellar populations. This feedback mechanism transforms a slow-growing galaxy into an efficient machine for rapid star assembly, solving part of the mystery behind the massive universe breakers. Some astronomers propose a radical alternative, conformal cyclic cosmology. This theory suggests our universe is not a one-time event, but one in an infinite series of aeons. In this framework, the end of one universe is linked to the Big Bang of the next. The crossover boundary acts as a bridge where physical conditions are reset. If this is true, the massive galaxies detected by the Webb telescope might not be new at all. We are witnessing a monumental shift in how we understand the early universe. For decades, our models favored a slow, steady buildup of cosmic structures, but the universe breakers have forced us to pivot toward a rapid assembly model. The early cosmos was far more energetic and efficient at forming massive galaxies than we ever dared to imagine. The James Webb Space Telescope is our primary window into this reality. By gathering unprecedented data, it challenges our existing textbooks and demands new physics. These massive galaxies are not just anomalies, they are the keys to unlocking the true history of our cosmos. They represent a frontier where our current understanding ends and the real exploration begins.